Question number 1. A temperature of 23 Kelvin is equivalent to, well, if 0 degrees Kelvin is minus 273 Celsius, then 23 would be equal to minus 273 plus 23, which gives you minus 250. So the answer is B. Next question. This one's tricky. Let's have a look. We have temperature and time graphs. Here we can see that the temperature at the lowest section is of a solid, because that's the coldest it can possibly be. And then you have this flat bit where you have a change in state. Okay, and this happens again up here. If we know that this is a solid, because that's the coldest part, we know that this will be a liquid. And then if this ever carried on, it would be a gas up here. And we have a couple of changes in state. Here, from solid to liquid, and here, liquid to gas. Now, if we can imagine that this is happening because you are heating up the solid at time t equals 0, you can basically imagine your heater. So here's your small heater connected up to the mains. You've got some voltage there. And your stop clock is counting time. As you start and time goes on, you're adding Q and the temperature is starting to go up. At the change of state, all that energy that's being given during that time, T, that Q, is being used to change state. And if we look at this section, it's not really changing state for very long. So that means during here, this section, when it becomes solid to liquid, it's actually not using too much energy because it quickly goes up and continues being a liquid. In this section, though, it's flat for ages. That means that the heater is on for a considerable amount of time. So, I know I'm going to this one first, the specific latent heat of fusion. Fusion is from solid to liquid. The time that that takes place for is really short, so you don't need much energy. And then the second part is the specific latent part of vaporization. That's up here. Time is much longer, so therefore this needs way more energy. Okay, so specific latent heat of fusion, is it greater than the specific latent heat of vaporization? No, it's not, because this one is way bigger. The second statement, the specific heat capacity of the solid is less than the specific heat capacity of the liquid. Let's have a look at that more closely. How can we tell from the graph? Well, the increase in temperature per second is telling you how much hotter it's getting. So how many degrees, or what the temperature is, how many degrees per second it's increasing by. If you have a substance that has a very high specific heat capacity, that means it needs a lot. Okay, so if the specific heat capacity is high, it needs a lot of energy to increase the temperature. So let's have a look at the solid. If we look at the solid compared to the liquid, in order to increase its temperature, it needs more energy than this one. How do we know? Because in order to go up, it needs less time than this one does. This one's going up at a much slower rate. So, in conclusion, the liquid has a higher specific heat capacity because in order to increase its temperature by the same amount as the solid, it would need a lot more energy. So the second statement is correct and the first one is wrong. And the only option is C. Next question. What is the temperature of an ideal gas a measure of? And you should remember, this is just a little factoid that you have to remember off by heart. The temperature is proportional to kinetic energy. Okay, and those two things are proportional and they go together, and you just have to learn it. Similarly, this is a learning off by heart thing. Which of the following is an assumption in the kinetic model of gases? You need to learn all your assumptions. And one of them is that the collisions between the molecules are elastic. What does that mean? That they don't lose energy. Because if you have a gas, a fixed volume of gas, and the particles are all zooming around all over the place, if every time they hit each other, they lost a little bit of energy, eventually they'd all end up in a pile on the floor because they would lose all their energy and just collapse. And that doesn't happen. If anything, they escape by diffusion, maybe, and spread out as much as possible. So you assume that the collisions are elastic, and elastic means they don't lose energy. This is a definition question, and definitions must be learnt. The specific heat capacity is the energy. I'll just write it down. Okay, the definition is specific heat capacity is the energy needed to raise the temperature of 1 kilogram of a substance by 1 degree Kelvin. Some of you forgot to say the temperature. So your definition read, energy needed to raise 1 kilogram by 1 degree. That's not enough. You must say the temperature of. Now we have some calculations. And we have a small amount of iron, which is heated up to 180 degrees, and then it's put into a beaker of cold water, like that. And the cold water, its temperature goes from 20 to 44. And what happens to the metal? Well, it goes from 180 down to thermal equilibrium. So eventually, this is one of the things that you need to assume, it will eventually have the same temperature as the water. So it will go 180 down to 44. Okay, so now let's try some calculations. What is the specific heat capacity of iron? Well, the Q, the heat energy that comes from the iron, ends up warming and heating the water. Okay, so what we have is energy lost by the iron is energy gained by the water. Now we expand this with an equation. We have M, specific heat capacity of iron, change in temperature, equals the mass of the water. So this is water, this is iron. Mass of the water, specific heat capacity of water, times the change in temperature of the water. Okay, oops, I meant iron here. So what I'm going to do is put all the numbers in. And here they are. So we have the mass of the iron, 0.58, the specific heat capacity we need to find, and the change of temperature of the iron in the water, which goes from 180 degrees all the way to 44. All of this energy ends up inside the water, okay? And that mass is 0.35 times 4,200 times the difference in temperature of the water that goes from 44 to 20, okay? And then you calculate all that and you should get 447.3 joules per kilogram per Kelvin. Don't forget units. I will, in the next assessment, start taking off marks for not having the correct units and not using the correct significant figures. Right, the next question is about your evaluation, and you really should have been thinking about this while you were doing your experiments. Why is the value likely to be different? And it's only asking you about difference, so you don't need to think about this too much. But if you think about it, is the energy that's inside that iron only going to the water? And it's not. Some of that heat from the iron is also going to the beaker. Some of it's going to the surroundings via evaporation. Now, it's not enough to say the water evaporates. You would need to say that the heat is lost and taken away from the water by evaporation to the surroundings. So, heat, thermal energy lost to surroundings. The beaker and the air. It's important that you are specific. So don't just say surroundings, you need to say where exactly it's going. More definitions. The question is about the change of phase of a liquid and latent heat of vaporization. What is the difference between evaporation and boiling? Well, evaporation happens at any temperature. Any. Okay? And boiling can happen only at boiling point. So be specific. Or in or throughout the liquid. And then up here, evaporation happens at any temperature on the surface. State the difference between evaporation and boiling with reference to surface area of liquid. Now you actually need to say, how does this affect evaporation and boiling? And you needed to say that surface area will increase evaporation, but not affect boiling. I think with most of you, you misunderstood the question. So what is specifically going to be the effect of increasing this one? Another calculation question, but this time it's about the specific latent heat of vaporation. So we have Q, the energy that arrives, equals the mass of liquid vaporizing times L. And this is like the kettle experiment that you did. So, just plugging in the values, how do we work out Q? Q is energy in joules. We don't have that value, but we do have power in watts and time in seconds. So if we multiply power times time, we can get energy. So you need to put both of those values in. 15 watts times 4.5, Okay, so this will give you your Q value equals the mass of the water boiled away, 1.8 times 10 to the minus 2 times L. Now here there's a bit of an issue, because if we have a look at the question, it's 1.8 times 10 to the minus 2, but on your paper that minus is very difficult to see, and in fact it looks like a plus 2. So I'm going to assume that you couldn't read the minus, and I'll proceed. So if you now work out this side of the equation, 15 times 4.5 times 10 to the 2, and divide by 1.8 times 10 to the plus 2, you should get a value of 37.5 joules per kilogram to the minus 1. Our last question, this one's a little bit different to the last explanation, because it asks you for you to explain one reason why the calculation is greater than the true value. So you need to be way more specific than before. Don't just say that Q is lost. You actually need to say that Q is larger because some of it is lost to the surroundings, to the beaker, air, etc., giving a much larger theoretical value. Okay? If you don't say that it's larger than it should be, then you're not explaining why you're getting a larger value of the specific latent heat evaporation. So you'd have lost 1 mark.